Welcome to our lecture on normal curves. This is probably the first lecture where I don't think anybody knows everything I'm going to say here. There's going to be some new things that nobody's seen before. So you really need to take some good notes on this lecture. Let's start with density curves. So a density curve is any curve that is always positive. That means it's always above the x-axis. So if you draw it, it's above the x-axis. The area under the curve is equal to 1. And that's really it. That's the definition of density curve. It's above the x-axis, and if I were to take the area underneath it, maybe with an integral, if you're familiar with that, then it would be equal to 1. What a density curve really is a theoretical model for a histogram. So imagine like a big histogram with lots of data and many bars. Okay, and they're all really small. If you were to kind of squint your eyes and you look back and you see the basic shape, well, if you trace that shape with a curve, okay, that's the density curve. And what we think about the area being equal to 1, the area under being equal to 1, is a little bit like saying that all of the observations are under the curve. Okay, so the number 1 is a bit of a stand-in for the number 100%. So if we look at the area underneath part of a density curve is equal to 0.3, that's 30% of the total. That's why we use the number 1. Okay, so here's a picture of a normal curve. You've seen this kind of picture before. It's often called a bell curve. You've got this equation up here, and we'll look at that on the next screen in a moment. But it's a very nice, smooth picture. A couple things to notice here is it goes off to the left and the right infinitely. Never touches the x-axis. It's impossible to show with the size of an ink pen or the pixels on a computer. Eventually, when you actually draw it physically, it's going to hit the x-axis. But you should know that it approaches in both directions asymptotically. You remember that word, asymptote. This is sometimes also called what we call a Gaussian curve, okay, named after the mathematician Gauss. He didn't come up with it, as far as I'm aware. He didn't even use it. But that's just one of the funny things about mathematics. Okay. All right. Couple things. I don't know why there are shadows here, but there they are. The normal curve is only normal in the sense that it is commonly used. Okay. There's nothing terribly normal about it. It's a weird thing. There's sound effects now. It's a density curve. Okay. The area underneath it is equal to 1. Here's the equation again. I'm not sure why there are sound effects now, so I'll turn off the sound. F of x equals 1 over sigma times the square root of 2 pi times e to the negative x minus mu squared all over 2 sigma squared. Very weird, okay? There are two parameters, mu, which is the mean, and sigma, which is the standard deviation, okay? And for every mean and for every sigma, for every standard deviation, we get a different curve, okay? So everything else in here are constants, right? Pi is just a number, e is just a number, x is the variable, right? You can't graph a function unless you have x in there somewhere. Okay, just like y equals mx plus b is the graph of a line, and yet somebody says, what is x? I say, well, x is the number we put in, the letter we put in there, so we're able to graph it. Okay, so really the only things that really can vary in a certain sense are the numbers sigma and the number mu. Okay, for every mean, for every sigma, and every standard deviation, we get something different. Okay, you can see like 3 slides called what is it? Okay, well, here's the mean in the middle, mu. Don't worry about the numbers in the x-axis for right now. Here's the number mu, the mean, the center, right in the middle. It's perfectly symmetric. If I go 1 standard deviation to the right, 1 sigma to the right, and 1 to the left, that's about how far away it's going to be most of the time. Okay, I'm trying to give you a visual picture of how big a standard deviation is on a normal curve. We look at this light blue region here. Okay, it's fairly large. I go 2 standard deviations to the right, and to the left, I can encompass this area. Okay, it's pretty nice. 3 would be right about here, 4, 5 is going to be out here. But it gives you a sense of, by the time we get to 3 standard deviations, the curve has gotten so close to the x-axis that visually it's going to look like it's hitting it, right? But once we go further out, this curve is still there, you just can't really see it. Really important point. Okay. Another point is that this light blue area is the exact same area as this light blue area. If I chop this thing in half, like that, okay, then this half of the light blue area will be the same as this half of the light blue area. Okay? All right. So shapes. First of all, what happens as the mean changes? What happens to the shape? Remember that the spread will remain the same if the mean changes. Okay? The area under the curve will still be equal to 1. It's an important point, right? So if the area remains equal to 1 and the only thing that's changing is the center, the entire shape shifts left and right. Nothing else happens. Okay. The picture, the actual shape of the thing remains the same. What happens as sigma, or the standard deviation, changes? Okay. So that means that this is my curve. Okay, this is my normal curve, and if the spread shrinks, if the standard deviation gets smaller, then remember the area underneath the curve must remain equal to 1. Okay, so that means that the area under the curve remains equal to 1. If I'm going to get tighter in like this, then the top has to come up, okay, to compensate, because I need the area to remain the same. Likewise, if the spread gets larger, then in order for the area to still remain equal to 1, to remain the same, then the top gets smaller. Okay. Okay. So a couple things. Why should we bother with it? Well, first of all, it approximates things that occur in nature. A couple things like biological characteristics such as height and shoe size. In general, if you were to make a histogram of heights of a population, it's not going to be perfect, okay, because nothing's ever perfect. But if I make a huge histogram with lots of biological characteristics, or rather with just height, then if I look at that histogram and I back up, it's really going to have that beautiful normal shape where it kind of falls off evenly on both sides. Shoe size will be the same thing. Error measurements. Okay, if I look at a test, error measurements. I'm sorry. Back to error measurements. If I step on a scale, scales are always wrong a little bit. Okay, and the issue is that the error can be really small, really big, and most of the time the error is very, very small, which means that nice peak in the center, but sometimes it can underestimate or overestimate. And those error measurements will fall off because most of the time an error is very small, but occasionally gets very big. Test scores. Now, test scores are not normally distributed typically. We often wish they were normally distributed because we make our lives easier as educators. But in general, that's just not the case. Okay, so that's where this next one comes in. It's a nice picture. Often we wish that test scores followed a normal model, and so you'll see people artificially put certain distributions on a normal scale, even though they don't really work that way. Traditionally, when people said curve a test, what they meant was take the distribution of test scores and artificially put them on a normal scale. So most people are getting C's. There's a few F's and a few A's. People don't really do that much anymore. When we say curve a test score, usually that's not what we mean. That's certainly not what I mean. But we often try to put things that aren't really normally distributed into a normal distribution. It's not a really good idea. Okay. Why bother? Well, there's a couple things. First of all, we need only two numbers to deal with it. Okay. If I tell you it's normally distributed, okay, and the mean is something and the standard deviation is something, then I know exactly what the curve looks like, right? So if I tell you the mean math score is 500, the standard deviation is 100, and the scores are normally distributed, I know everything I need to know about that distribution. You don't have to give me a list of hundreds and thousands of numbers, hundreds of thousands of SAT scores. I know really anything I need to know about that distribution. Here's a picture of that. A mean of 500, a standard deviation of 100, so I go to the right, and I go to the left, 100 in each direction, okay? That's my normal distribution, okay? 200 to the right, 200 to the left. Remember, it falls off at the same rate as before, except that now instead of having mu and mu plus sigma and mu minus sigma, I have actual numbers in here. Another thing to notice here that I didn't mention before is that if I take a look at the point right above one standard deviation to the right, not a very good line, right above one standard deviation to the left, oh gosh, that's terrible, and I look at this intersection point, it should really be right about there, should be right about there, okay? This, for you calculus people, this should have intersected up here is what I'm saying. That's your inflection point, okay? So if that helps you understand what's going on here, then awesome. But otherwise, don't worry about it too much. So what I want to erase it. Hidden. Nope. That didn't do it either. Okay. Here we are, back again. Okay. So that's well and good. We have our picture here. All right. So here's the upshot. Why should you care? Okay. And it's unfortunate that you can see the shadows, but that's okay. Why should you care? It's a good question. I've given you all this information. Here's a reasonable question. how many or what percentage of students score between a 400 and a 600, and I can tell you right away that it's 68%. That's kind of a big deal. All I had to know was the mean, the standard deviation, and the shape of the curve. I could automatically rattle off, without thinking about it, what proportion of students are going to score in that region. Right? So if you're trying to get a sense of what's my likelihood that I'm going to score between a 400 and a 600, automatically we know that. Okay? And the question is, how did I know that? And I'm going to show you how I knew that. Okay? This is a very powerful idea. If I just tell you the average income is $40,000 a year, and the standard deviation is $8,000, you can't tell me anything because you don't know the shape of the distribution. But if I told you that we're a normal distribution, you would automatically have all kinds of information that you could learn. Okay, so let's take a look at how I knew that the area, or rather the percentage of students who are scoring between a 400 and a 600 in SAT math is 68%. And I'm realizing as I'm doing this example now that the SAT has obviously changed their scoring scale, so that it's no longer on an 800-point scale. It may be that every section is, I'm not sure. But in any case, 600 is not a bad score on this SAT scale. All right, so here's the important rule. It's called the 68, 95, 99.7 rule. You need to have all this in your notes, but if you really need to have this one tattooed on your forehead or something. Okay, well, not on your forehead because you can't read that. Maybe on your wrist. Okay, but this is a super important concept. By some people, this is called the empirical rule. Okay, in AP statistics, we often call it the 68, 95, 99.7 rule because, just like the 1.5 IQR rule, if you memorize the name of the rule, you've memorized the rule itself. So we'll call it the 68, 95, 99.7 rule. All right, here's the idea of this rule. Okay, okay, that the area between one standard deviation to the left and one to the right, the proportion is always 68%. As long as you know it's a normal curve, and I go one standard deviation to the left of the mean, one to the right of the mean, 68% are in there. Two standard deviations to the left, two to the right, 95% are in there. Three standard deviations to the left, three to the right, 99.7% of all scores will be in that region. Okay. Notice there's 3% left, 0.3% left over. So this rule could continue forever. It's not going to. I mean, we only use it up to 3 standard deviations. After that, you've gotten most of the data. But always remember that you can go 4 standard deviations. There's still data left over. There's always still data left over. Okay, so let's look at this picture again and try to figure out how it applies. Notice the mean is still 500. Standard deviation is still 100. This is still the SAT. So I can tell you that 68% of people who take the SAT score between a 400 and a 600. I can also tell you that 95% of people who take the SAT score between a 300 and a 700 because 300 is 2 standard deviations, 2 100s less than 500, and 700 is 2 standard deviations, that's 2 100s bigger than 500. So if I go 2 to the left and 2 to the right, I've got 95%. If I go 3 to the left, okay, that's 200 to 800, then we have 99.7% of people are going to score in that range. Okay, now notice that 800 is the maximum score of the SAT, and I don't know actually if you can score 100 on the SAT. That may actually be impossible mathematically, to tell you the truth. But in any case, there's some slop here, right? Remember, the SAT is a scale that goes from 0 to 800, even though we know that normal curves go off infinitely both directions. That's okay. Okay. Just remember, there's always going to be a little bit of error with these things. So if I look from 200 to 800, 99.7% of people are going to score between 200 and 800. Okay. This also means that since this is a symmetric curve, okay, if I know that 68% of people are scoring between a 400 and a 600, I can tell you 34% of people are going to score between a 500 and a 600. Pretty cool, right? Now, we can't divide it up any more than that because I don't know what happens between 500 and 600. But I can chop these things up any way I want as long as I'm chopping it up at the center, at the mean, and at all the standard deviation markers. Okay, so I can chop it up any way I want. I can find out what proportion of people score between a 600 and a 700, or a 400 and an 800. I can do all of that. I just can't chop it up in between the standard deviations. So the empirical rule, the 68, 95, 99.7 rule, is super, super useful for getting a general sense of how these distributions work. Okay, and it's going to be very, very useful for us. We're going to practice with these a lot, and normal curves are going to get more and more interesting and more and more. They're not going to get much more complicated, frankly, but they are going to get more interesting. And having a deep understanding of this is essential for the rest of the course. So you really need to make sure you're on track with this. All right, that's all I got for today, even though it was quite a lot, I'm sure. Take care.